All right, here's part two of today's lesson. So we're going to look at this next example. We're going to draw a scatter plot and align a best fit for the data chart below. All right, so we've got distance and we've got time and we've got our chart right here. Okay, so there's a couple of different things that we need to do first. Let's figure out which one is the independent, which one's the dependent. All right, what are we thinking? Evie, what are you thinking for distance and time? Which one's independent? Which one's dependent? Yell it out. All right. So yes, we should be looking and seeing that time is the one that just keeps on going on and on and on. This is independent because it just keeps on going. Time just goes on and on and on. But the distance will always depend on your time. Now, knowing this, which one's X and which one's Y? What are you thinking, Emma? Yep, time's independent and distance is dependent. Our distance here or in this column is always our y and this first column is always our x. All right, let's go and graph this on our chart right here. So we have y to the sky, x is down here. So we want to write our time and this is in seconds. And then here we have our distance in meters. Okay, what we're also going to do here is we're going to find the mean data point. Mean just means average. So we're going to find the average point. So we're going to find the average. We have to add everything up and divide by how many there are. So we've got 1, 2, 3, 4, 5, 6, 7, 8 pieces of information here. Let's go ahead and add them all up. So it's like finding the average is called the mean. So 0 plus 2 plus 3 plus 5 plus 6 plus 7 plus 9 plus 10. That gives us 42. And we're going to divide that by 8. So there's 8 pieces of data. Let me just double check that again. Yeah, and we're going to divide by 8. And we get 5.25. So that's our point that is the average of all of the times. And then we're going to do the same thing with the distance. So we're going to add these all up. 10 plus 20 plus 30 plus 40 plus 50 plus 60 plus 70. And we get 280. And what do we do with that number? Divide it by 8 again. And we get 35. So this is a point that we are definitely going to graph. And we want our line of best fit to also go through that point because it is the average point out of all of our pieces of data. Okay, so let's go ahead and graph. So we're going to start at 0. And I told you a little trick the other day. In order to figure out the scale, you want to find the lowest number. So the lowest number looks like it is 0. You want to find the highest number. So we are still plotting our data. So we were finding the lowest number and the highest. And then we want something, a scale that's in between there. So it looks like we could probably go every 2 spaces and go up 1. I think that should be enough, but let's count it first. So that would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that works perfectly. So you always want to kind of like check it first before you start scratching in all the numbers, right? Because you don't want to get up to, oh, it only goes up to 9. Like that doesn't work. And then you'll have to go up by 1 space. What's nice is to have your scale go across to kind of cover as much ground on the chart as possible. Right, same with this. It looks like maybe even going up by 10s here. And let's count it first. Let's see if we can make it 10, 20, 30, 40, 50, 60, 70, 80. Yep, it looks good. So if we go up by 10s every 2 spaces, so that'd be 10, 20, 30, 40, 50, 67, 60, 70. And let's just throw one there. So we looked at the lowest, so we definitely need 0. There's no break in the problem here, and we need to get up to 70. All right, so let's go and graph this information. We also want to graph our average point as well. So at 0, 0, we have a point, over at 210, 320, and then watch out, there's no 4, so just go over to 5, 6, 40, 7, 50. There's no 8, so skip it over 9, 9, 60, and 10, 70. There we go. So we've got our scatter plot, and we're going to graph our mean point as well. So that's at 5.25. So 5.25 and 35, which is right around here. That would be our average point, or mean data point. And we definitely want our line of best fit to cross that piece of data. There we go. Do we have the same number of points above and below? Yeah, it looks like there's 2 above and below. Our point is going, our point that's our mean data point is going through the line of best fit. Our line of best fit is, it looks like it's direct. It's also looks very strong. Oh, I'll have to write it right there. Maybe a title would be nice right here. Distance versus time. It's definitely strong. It's definitely positive. And our last word that we're going to say, what do you think, Mateo? Linear. All right. Okay, so we are going to determine the equation of the line of best fit. So the first thing we need is the slope. We also need a point and then our equation. All right, so we have a whole bunch of points here that we can pick from. We can also try to find the slope. The slope is found by taking any 2 points that are on the line. So not any 2 points that are on here, but any 2 points that are on the line. So we can even grab these 2 points that are on our line right here, or even our average point too, and then we can find the slope. Again, everyone's line of best fit might be a little bit different. It just depends on how you drew it. But mine has a slope of 1, 2, 3, 4. So I know I'm going to rise over run. I'm going to rise 4 and run 1, 2, 3, 4, 5, 6. Well, I purposely just made a mistake. Can you figure it out? Can you figure out my mistake? Right. Well, if you guess that the slope is not 4 over 6, you're correct. It is not 4 over 6. Let's go back and look again. So when we're looking at, we're not just counting by squares. What we're actually doing is looking here at our distance, right? The distance here goes between 20 and 40. So how much space is there? Well, this is actually 10, 20. The rise is actually 20. Well, the run, again, we're going up by 2 squares for each space here. So it's 1, 2, 3. It's rise 20 over 3. All right, and then we're going to also pick a point that's on our line. We can pick even the average point if we'd like. It doesn't matter as long as the point is on a line. I think I'm going to pick this one, 6 and 40. All right, so let's go ahead and fill in our equation. So our equation is y minus y1 equals m, x minus x1. Hey, that looks a lot like our last unit where this is x1 and this is y1 and this is our m. That's our slope. We know this is all frozen here except for the m, the y1, and the x1. So m, we're going to have 20 over 3. Here we have x minus 6. All right, what happens to negative 40? It jumps over and it becomes a positive 40. We're also going to there. What do we do here, Ava? Yeah, we distribute. So y is equal to 20 over 3. x. Well, that's a 3. And then here we have 20 times 6, and then 20 times 6 divided by 3. We get 40, so here we'll have negative 40 plus 40. All right, and we can see that these two values cancel each other out, so that's negative 40 plus 40, and we get y is equal to 20 over 3x. Hey, and as it should be, it is direct, right? It is a direct variation, so we shouldn't have a b value here. It's going through the 0. All right, so we're going to make some predictions now. So using the line of best fit, we're going to either interpolate or extrapolate. So using the line of best fit, we're going to determine the time it will take to cover 55 meters. So 55 meters. 55 meters, we can tell from right from our data set that 55 meters is in between 50 and 60, so that this is called interpolation. We are going to interpolate because it's inside the data. So 55 meters is inside the data. It's between 50 and 60. And what number is between 50 and 60? Well, we're going to get from the graph, we can see that it's go over to 55, right? So go over to 55. This is 55 right here. Hit the line and go right down. So it's around here. So you want it to be, would assume that it is 8, right? You think it's 8, but it's not. It's a little bit more than 8. We can see that right from our line of best fit. So you go right across and down. And it's not 8 because this is not a linear, like, well, this is a linear function, but it's not a perfect, right? We can tell by the slope it is not a very even kind of slope. So yeah, we're not going to get like that perfect result here. It's a little bit more than 8. You say maybe like around, so we could do like a little squiggle there, approximately 8 seconds. And then, but from the equation, we have our equation, y is equal to 20 over 3x. Now we can actually insert this 55 meters, and we got to figure out which one are we going to put it in for. Are we going to put it in for x, or are we going to put it in for y? Now 55 meters is meters, that's distance. And which one's distance? Is it x or y? Well, distance is y. So we're going to sub it in for y. We'll get 55 here is equal to 20 over 3x. We have to multiply by 3 on both sides to get rid of those 3's. So we get 165 over here is equal to 20x, and divide them both by 20. And here we get x is equal to 8.25. There we go, from the equation. And then our last question here, we're looking for 12 seconds. So let's go back up to the chart here, and we can see that, well, 12 is off the chart. So it's somewhere around here. And if we extended our line, it's going to be somewhere around here. So maybe around 80. So we would go up from 12 and over, and it's like a guess, right? It's about 80 seconds, or sorry, 80 meters. But from the equation, we can actually figure it out more than just an approximate. So we would sub in 80 for x, and here we get, or sorry, sub in 12 for x, and here we get y is equal to 80. So it is actually 80. Wow. And here we are extrapolating because it is outside the graph for the data. All right, for the last page, we are not going to look at the line of best fit for using technology, so no worries about that. But give this bottom part a read here to figure out what's a good line of best fit. So I just want to direct your attention to some R values. So if the R value is close to 1, it's going to be strong, but it's almost 0, that means it's going to be weak. And we can tell that from our data scattered all here. So R value that is around 0 is weak, but if it's around 1, it's strong. All right, see you tomorrow, and please work on the homework, and yeah, we'll see you tomorrow. Bye.